Alright, today we're going to continue with our simple harmonic motion, and today we're going to look at springs. So yesterday was pendulum swinging back and forth. Now we're going to look at oscillating springs that are going to go back and forth, and we're going to look at different formulas and different topics that apply to springs. So to start with, we're going to look at a couple of terms and get to the basics here. So when we stretch a spring, it's going to have a restoring force that pulls it back. So you can see in this case we're going to expand the spring, so the spring is going to want to snap that thing back towards equilibrium, or if we compress the spring, the force is going to want to push it back outwards. And Robert Hooke actually figured out this formula, and it's basically similar to force equals mass times acceleration, except in this case it's the strength of the spring that's doing the force, and the further we stretch it, the larger the force is going to be. So he basically determined that we can calculate the amount of force by whatever the spring constant is, so that's usually given to you in a question. So a spring of constant of like 5 would be a pretty weak spring, something like 500 or 1,000 would be a pretty strong spring. So they'll give you that number, and then x is our distance we stretch it or compress it. It works the same either way, and that's it. So in this case, if I compress this spring from equilibrium 5 centimeters, we would put 0.05 in our formula. It has to be in meters. And the negative sign in the formula just basically means that the force is pulling it in the opposite direction. So if we stretch it to the right, the force is going to pull it back to the left. Or if we compress it to the left, the force is going to extend it to the right. So let's use this formula just to see. So our first example we'll look at here is we have a mass hanging on a spring. So we got our spring. So normally if our equilibrium was in a certain position, but now we hang a mass on it, and that's going to stretch it down further. So in this case our spring K is 38.9, that's given to us, and we have a 1.3 kilogram mass, so we should be able to figure out the distance it's going to stretch. That's what we're looking for in this case. So the trick to this one is we basically have force of gravity pulling this thing down, and then we have the force of the spring. We call it Fs, or I'll use Fk. So the force of the spring is what's pulling it back up. So if it's stretched, that means those things are balancing out. So we can just simply use our normal formula of mass times acceleration and make that equal to our new negative kx formula. So we have our mass is 1.3, we have our acceleration of gravity would be 9.81, we know the k is 38.9, let's keep the negative on there, and let's solve it for x. So it's a pretty easy calculation. We can go 1.3 times 9.81 and divide that by 38.9, and that gives us an x of negative 0.33. So that's in meters, or it would be 33 centimeters would be the stretch. So it's pretty simple to make the two equal to each other, and we can solve for the x distance like we did in this case, or if we didn't know what the k value is, we could measure that x distance and then rearrange it and solve it for k, and that would tell us how strong that spring is. So when we hang something on a spring, that's what we were just looking at. So remember our equilibrium, when that thing isn't moving, that is our new equilibrium position. And then you can see it's just going to bounce back and forth. So you can see in this first picture, our two forces are equal. So that's in equilibrium. If I stretch this thing downwards, and now our force of the spring is bigger, it's going to want to pull it back up. When it gets back up to the equilibrium position, it'd be equal again. Once it compresses, our gravity and our spring force are now both pointing downwards, and that would push it back down, and it would just keep oscillating back and forth. So if we continued this pattern, our spring would go from A to B to C to D. It would then move back down to equilibrium, it'd move back down to B again, and then it would go back up to C, our equilibrium, and continue. So it basically just keep repeating over and over that same pattern until friction or whatever would cause it to stop. So since we have a restoring force, we have that kx force, we can actually calculate the acceleration as well, using the same formula, mass times acceleration. So in our first case, we were using acceleration of gravity, because that was what we were trying to figure out how far the spring was stretched. But once it's stretched, that's the new equilibrium, so we're not worrying about gravity anymore, we're worrying about the actual acceleration of the mass on the spring. So we can basically redo that same formula and actually solve it for A. So negative kx over m would give us the acceleration. So let's do a quick calculation. So in this case we've got the k value is 55, they tell us, and our x is 18 centimeters, so put that in as meters, and our mass is 500 grams, let's put that in as kilograms, and multiply that out. So 55 times 0.18 divided by 0.5 gives us an acceleration of negative 19.8. So pretty big number. Let me try that again. That seems a little bit off. Yeah, well, that's right, 19.8. So we have an acceleration of 19.8 meters per second squared. So what that means is that's the acceleration at the moment it's released. So let me go back to this previous diagram. So if we look at this location, let's suppose at B. So let's suppose we pulled it down to B. As soon as we let it go, the spring's going to snap it back. So that would be the acceleration right at that initial release. And obviously it's going to get less and less as the mass goes up. And the only reason, again, it's negative is if we're pulling it down, the direction is going to be upwards. So that negative is just indicating a direction. So let's try the same thing, but now we're going to compress the spring. So it works out pretty much the exact same, except we're going to compress it 12 centimeters. And let's say the stretching distance was positive, so we can actually indicate the compression as a negative. And divide it out again, so 55 times 0.12 divided by 0.5, that gives us 13.2, and in this case it'd be positive. And that again is just indicating direction. So in this first case we stretched it to the right, so our acceleration was to the left. And in this case we compressed it to the right, or to the left, so our acceleration then would be to the right. So the plus and minus is direction only. You don't really need to worry about it too much. So since we have acceleration and we have force, and if it's accelerating, we're also going to have speed and velocity, and we know that there's energy. We have kinetic and potential energy of the spring. So let's figure out what the potential energy is of something stretched on a spring or compressed on a spring. And if we go back to like we did before when we were doing work, remember if it's constant we would just get a graph of force times distance. So our work was just force times distance, but in most cases it's not going to be constant. So often we'd have something like that. So then we'd use our area under the graph to calculate our work. So we're basically doing the exact same thing here, except our distance now is our stretch of the spring. So our force is k times x. Our distance that we're stretching it is x. And because it's going to be not constant, we'd have a triangle type shape. It's going to go from zero potential up to maximum and then back to zero and so on. So we'd get a triangular shape in terms of a graph. So our area of this would be length times width, or for base times height. So we'd have kx times x divided by 2. And we can rearrange and simplify that to be 1/2 kx squared. So our potential energy for a spring looks a lot like 1/2 mv squared, but it's not kinetic, it's potential, 1/2 kx squared. Okay, and the k and the x still mean the exact same thing. So let's do a couple quick examples of that. So potential for spring, 1/2 kx squared, 1/2 times k, which in this case is 15, and we stretch at 0.75. We don't need to worry about direction this time because it's going to get squared anyway, and energy is a scalar as well, so we don't really care too much whether it's positive or negative. So in this case we have a potential energy of 4.2, and energy, remember, is in joules. So that means that's how much energy that object would gain once we stretch it, and just like before, we can actually convert that to kinetic. So we can take that amount of current to kinetic. So let's suppose we wanted to do that calculation. Let's determine how fast that thing could go by converting it. So we'd have 4.2 joules. That would equal 1/2 mv squared. So if we knew the mass of the object, we could use that to solve for speed, just like we did in the previous unit. And that's what our next topic we're going to look at is, because this thing's going back and forth, it's going to accelerate, means it changes speeds, which means we're going to have speeds throughout the whole thing. So let's kind of look at a few different scenarios. So when we have the spring being stretched, let's look at that. So let's suppose this is equilibrium, and we're going to stretch at a certain distance. So at equilibrium, we'd have zero potential. Once it's stretched, we're going to have maximum potential. And because we have potential, that's going to be where we're going to have the most energy, which means we're going to have the most acceleration. So once we let that thing go, it's going to have the most acceleration. And as that moves, all that energy is going to get converted to kinetic, which means all that acceleration is going to cause that thing to speed up. So that means our velocity will be maximum as well. So it kind of works opposite. So once it's stretched, we have no kinetic and all potential, and we have lots of acceleration. When it's back to normal, we'd have all speed and kinetic and no potential, and basically zero acceleration. So those things kind of work out the same, but just opposite to each other. So when we're at equilibrium, all of our energy is kinetic, which means we'd have the most speed. When it's at stretched out, we have just potential, which means our speed would be zero. So we can take our kinetic and potential formulas, we were just looking at that on the previous page, and let's rearrange that and rename it slightly. So our x is our distance we're stretching. Our maximum distance we're going to call that the amplitude, which is just like we did before with circular motion, or what we're going to do with waves as well. The amplitude is the maximum distance from the equilibrium to the biggest part of the cycle. So that's our biggest distance. We just use a instead of x, but it's the same measurement. And make them equal to each other, and let's solve for v. So if we cancel out the halves, bring the m over, so you'd have ka squared divided by m, square root both sides, and because it's a squared and square rooting, we can actually simplify it to be a equals k over m. So really all we need to calculate the maximum speed is the k, the spring constant, how far we're stretching it, and what the mass of that object is on the spring. So let's try that for this one. So we're going to stretch it 13 centimeters. Our K value is 367, and our mass is 17 kilograms. So that means at equilibrium, once it's stretched and released, once this thing gets back to equilibrium, that's when it'll be traveling the fastest. So we can do this calculation, we get 0.6 meters per second. So it'd have a zero speed when it's stretched, and then once it goes back to the equilibrium, that's where it's going to get the largest velocity. And then it just repeat. Once it gets compressed, it'd go back to zero, then it's going to shoot back out, and it'd be back at 0.6, and then it would slow down to zero, and it just keeps going back and forth between 0 and the 0.6. One last formula to look at, and that's period. So just like we had for period of a pendulum, it works the same. And we can actually see that our circular motion speed formula actually applies to this scenario. The only thing that's different is instead of it being a radius of a circle, we're going to use amplitude. And we're going to use our formula we just had for Vk max, the a square root k over m. Make those things equal to each other. You can see the a's would cancel. And we rearrange the formula to solve for t. We get 2 pi m over k. And if you remember on pendulums, it was L over G. So it's almost the same sort of formula. It's just that one is a pendulum, so we have length and gravity, and when we're dealing with springs, we have mass and spring constant. Both of those formulas are on your formula sheet, so you just got to remember which one's which. Anytime you see a K, that's obviously going to be a spring. So let's do this last question. So 2 pi square root m over k is our formula. We want to solve for period. So we'd have 2 pi times 17 over 367 square rooted. So just type that in. And we get an answer of 1.35. So that would be 1.35 seconds it would take for that thing to go back and forth, like one full motion of compression to expansion, and that's it. So you can see springs pretty straightforward, and like I said, really the only thing that's different is we're using different formulas. So all of your K formulas or A's, when they're talking about maximum velocity, things like that, those are all dealing with springs. But they're all on your formula sheet. You should find it pretty easy to calculate.